History Physics.
This is the 2016 Regents Exam in Physics. We're going to start out with a multiple choice, and maybe I'll make it to the other parts. But one thing you should know about the multiple choice is that students lose most of their points in the multiple choice. Now, granted, it's got the most questions in it, but I think maybe just as important is the fact that because it's multiple choice and you have the answer in front of you somewhere, the correct answer, you decide you're just going to circle one. Don't cut corners in the multiple choice. Draw your pictures. Do everything you're supposed to do. Treat it like a long answer problem, and then just circle the right answer that's there. So let's start off. Now, I was not able to annotate these. YouTube has gotten rid of annotations, so you can't click on them like I did on the old ones. But I do have a list of time codes, so you can just jump to the problems you're interested in. But keep in mind that I usually, even if you know how to do a problem, if you want more information on a topic, I will very often go into more detail on that topic when that question comes up. So let's take a look. Number one, which quantity is a vector? Let's see. What is a vector? A vector is something that has both magnitude and direction. And now when we look at number two, we got power and kinetic energy. Now, one thing you need to really understand, one of the beauties of energy, one of the reasons it's such a nice thing to work with is that it's a scalar. A scalar is just something that just has magnitude. So the nice thing about energy is you don't have to get into complex vector addition, because vector addition can get involved. Kinetic energy, no, that's energy, so that's out of the question. And power, what is power? Power is the rate at which energy is used. They give it to you something like that on the Regents reference table. So power isn't it, because that's kind of related to energy. Well, very much related to energy. It's the rate at which energy is used. Now speed, this is just something you have to kind of memorize. If something has speed, it also has velocity. Now velocity is a vector. Speed is not. Now, why do we even need speed then? Because sometimes you want to describe something that is going at a constant speed, but it's not a constant velocity. For instance, if you're going in circular motion, right, like that, we're going around a circle, that's a bird's eye view, and here's my object. At this moment in time, the velocity is that way, right? And it also has a speed. Let's say it's going 20 meters per second. When it's up here, it's still going 20 meters per second, but now it's going this way. And if these are velocity vectors, these velocities are different, but the speed is the same. So that's why we need this idea of speed. So speed is a scalar, right? Speed is a scalar. One easy way to remember that is speed scalar, velocity vector. You just somehow have to memorize that because that's what that's all about. All right, so speed is a scalar. Weight. All right, I'll wait, but we don't have all day. Weight, of course, let's get in. When do we ever see weight? We see that with our free body diagrams or something like that. A lot of times we may have something like something on an inclined plane, and we circle the object of interest, and we draw our vectors, and we say, oh, let's see. We're going to draw a free body diagram. We're going to circle the object of interest. What's in contact with this? Well, we have the force of friction up the ramp, and we have the normal force, right? The ramp is pushing up. It's also doing that. And then we also have the weight, F sub g. So that is a scalar, right? I mean, not a scalar. That is a vector. And, all right, see, we've drawn it as a vector. So weight is a vector. Weight is a force, right? It's the force due to gravity, F sub g. Force caused by the phenomenon of gravity. All right. A 65 kilogram astronaut. All right. They gave us the mass. We need to understand our units. So when they say 65 kilograms, they gave us the mass. weighs 638 newtons. 638 newtons is how much is being pulled down because the guy's got stuff or the woman's got stuff, whatever kind of human being it is, has stuff. And because they have stuff, they're attracted to other things with stuff, like the planet Earth, terra firma. So it has weight, and 638 newtons of weight at the surface of the Earth. All right? What is the mass of the astronaut at the surface of the moon, where the acceleration due to gravity is 1.62 meters per second squared? Now, this is what some of you might call a trick question. I don't really call it that. It's testing. Do you know what mass is? It's an obvious answer if you understand what mass is. Mass is how much stuff something has. And this astronaut had 65 kilograms of stuff, just like this marker has a certain amount of stuff in it. And if I take this anywhere in the universe, it will have the same amount of stuff. Now, whether it pulls down the same amount as pulling down on my hand, whether it pulls down as much depends on its weight. Weight is the pull, and mass is the stuff, right? So it has the same amount of stuff. So let's see. What is the mass? It's 65 kilograms. Choice two. 65 kilograms is the astronaut's mass wherever, even in Alpha Centauri or Hornley von Stingblaisdalchen. Plim. When the sum of all the forces acting on a block on an inclined plane is 0, the block, all right, well, this is the idea of equilibrium. When the sum of all the forces acting on a block on an inclined plane is 0, I assume they mean the vector sum. The Board of Regents in their infinite wisdom decided to just say the sum of all the forces. That's a little sloppy if you ask me. But anyways, I assume they mean the vector sum. So they're saying if I got, let's see, it's on an inclined plane. All right. So I got an inclined plane and let's say it's sitting on the inclined plane and nothing's touching it. And I'm going to circle the object of interest. And remember, with our inclined planes, we're going to want to tilt our axes like this. I'm going to make this the y-axis. This is the x-axis. I'm going to use the particle model. I'm going to put a particle right in the middle, right there. And let's see what are the forces. I circle the object to see what's in contact with it. And it looks like the only thing in contact with this block is the inclined plane. So let's see what we have here. Let's see. It kind of wants to slide down that way, but it said it's at rest, so there must be a force of friction opposing the motion. That is static friction, the most complex of all of the frictions. We'll get into that later, I'm sure, though. We got friction going up, and we also have the surface is pushing up. Like that, it's pushing up on there, and that's the normal force. Normal, of course, means perpendicular. It's the force that's perpendicular to the surface. They call it a normal force. I believe it's the mathematical term, actually. Normal, right? All right, so we got those two forces. Those are the only contact forces because I see nothing else is in there. The only thing, whenever there's a contact force, if you circle the object of interest, the whatever's in contact must intersect the circle. And I see the surface is the only thing that is doing that. All right, what else do we have? Forces at a distance, we have the force of gravity. Like that. All right. Well, those vectors must add up to 0. And if the sum of the forces, the vector sum of the forces equals 0, this could be doing one of two things. It could be at rest, or it could be at constant velocity. Right? Velocity. Now, let's take a look at this. Since we got our inclined plane here. What we would do to analyze this problem, of course, is to break this vector, the weight vector. Oh, that's a terrible one. Here, let me try this better here. Oh, yeah. Oh, that's good. That's good. That's solid. All right. So this is Fg in the y direction, and this is Fg in the x direction. If all the forces are 0, then this force, Fgx, must be equal to the force of friction, even though I didn't draw it very well. Let me redraw my force of friction there. What do we got? Like that big. All right. So that one equals that one, and this one equals that one. That thing's in equilibrium. the vector sum of the forces is 0. And when the vector sum of the forces is 0, it's either at rest or at constant velocity. We know Newton's second law says the sum of the forces equal mass times acceleration, right? And if they're equal 0, there is no acceleration because this side is 0, so the acceleration must be 0. We know the mass isn't 0. So this is either at rest or constant velocity because it's in equilibrium. Let's see. Number 1, must be at rest. No, it must not. It could be moving at constant velocity. Must be accelerating. It's not accelerating. Maybe slowing down. Nope, that would be accelerating. Maybe moving at 4. 4. It may be moving at constant speed. Right? If it's moving at constant speed, it must be moving at constant velocity in this case because it's in equilibrium. All right, there we go. Number 4, the greatest increase in the inertia of an object. Well, I can tell you the answer right now. Inertia is a property of matter in which, because things have mass, they have a reluctance to change their motion. If they're already moving, they want to keep moving. If they're at rest, they want to stay at rest, right? So inertia is dependent on how much stuff they have, how much mass they have. So if we want to increase the inertia of an object, we have to increase its mass. Like if it's a hunk of clay, you better slap some more clay on that because you need more stuff. All right, what do we got? 1, increase the mass of an object to 1 to well, we just doubled the inertia because we went from 1 kilogram to 2 kilograms. That's looking, well, we'll see what else we have. Net force applied to the object from 1, forces have no impact on the inertia. Inertia is just a function of how much mass the object has. The time that the net force, what time? No, speed of an object change, no, the answer is 1. You have inertia, more mass, more inertia. Less mass, less inertia. Same amount of mass, same amount of inertia. See the trend there? All right. 5, a 100 kilogram cart accelerates at 0.5 meter per second squared west as a horse exerts a force. All right, we got to draw a picture. Make sure you draw pictures. You got to draw pictures. I want to see you let your freak flag art thing fly on this. Okay, make sure you're drawing pictures. You're not drawing pictures. You're just not even trying. You might as well just go home. If you can't draw a picture, I don't even know why you're here. I just leave. In fact, if you're not drawing pictures now, just leave. Turn this off. You make me sick. We have a cart. 100 kilograms is that cart. And we got a horse drawn on there. Let's see. There. I was a little worried about that horse. I was okay drawing the cart. But I was thinking, man, I don't want to draw a horse, but actually I did a pretty good job. Yeah, it's a good horse. All right. So the cart is accelerating this way. We're going to go east, west. All right. Generally, we want to go, usually just for consistency, let's always make that direction east, left, east, right, east, left, west. And also, what we're going to do is when we draw a coordinate system, remember, we're going to have x and y. So this will be positive x, positive y, negative y. And also, this is going to be east, and this would be usually north, and this would usually be south, and this would be west. And, of course, positive in this way, positive, negative, negative. Right? So that'll be our convention so that we can automatically just answer questions and keep our vectors straight. This is about getting our vectors right. So the horse is applying a force. I'm going to apply the force in red, right? So the horse is applying a force this way, right, by pulling on it, and that is 60 newtons. 60 newtons. All right, so force the horse on cart equals 60 newtons. All right. What is the magnitude of the force that the cart exerts on the horse? All right. So they want to know the force that the cart on horse. What does that equal? And actually, I wouldn't say that was 60 newtons. I would say that's negative 60 newtons because that's in the negative direction. All right. Well, the horse pulls on the cart. What does the cart do? The cart pulls on the horse. All right. So here's I didn't finish my connector rod harness situation there. Yeah, that's how we connect to a horse, of course. And so what's the force that the cart is pulling back on? Of course, this is Newton's third law. 60 newtons, 60 newtons. It's equal in magnitude, opposite in direction. I push on you, you push on me. Who pushes harder? It has to be the same. That's the brilliance of the third law. It wasn't so much that forces come in pairs. I mean, if I push on the wall, it's kind of clear to everybody the wall pushes back. But what was brilliant about Newton's observation is that the forces are equal in magnitude, opposite in direction. That always occurs. That's Newton's third law of motion, right? So anyways, they threw a lot of extra information at you on that, but that's all you have to do. No calculations, just understanding of physics and understanding of the third law. Where it really gets confusing is like, the common example of the mosquito splattering on a windshield. You think that the mosquito felt a greater force in the windshield. It didn't. It's just that the windshield can handle the force that more force than the mosquito can. So it splats. Their forces are actually equal. All right. What do we got? That's number 6. So that was choice 3. 3. All right. 6. No, that's 5. That was 5. 5 was 3. Number 6. Let's take a look at 6. Sound waves. Sound waves. All right. Are described as... All right. What is sound? Sound is like you can hear me right now. What's happening? Well, I got these vocal cords in here. I got these muscles flapping back and forth. In fact, when you talk, you feel it vibrating away. And what that's causing is air molecules to vibrate. And then they start vibrating and they go out in all directions like this in 3 dimensions. You can't really, I wish you could see it. It would be something to see, but we can't see it. We can hear it. It goes in all directions. That's why wherever you are in the room, you can hear me, right? So, now, all right, so mechanical can describe, what is a mechanical wave? We need to know what these words mean. A mechanical wave, mechanical. Mechanical requires a medium. A mechanical wave only exists in a medium. It needs something to vibrate. These waves are vibrations, something's vibrating or oscillating. In this case, a mechanical wave, like a spring, you got a mechanical wave and a spring. Without the spring, you don't have a wave. So the spring is the medium. So a mechanical wave requires a medium. Now the question is, does sound need a medium? Well, we know that sound does travel in air. That's how we're used to it. It also travels in water. It seems like it doesn't travel as well, but it actually travels better in water than air. It's faster and I believe more efficiently. It's just that our ears aren't designed to hear underwater. So when you're underwater and you're hearing that stuff, it doesn't sound so good. So it travels in water, travels in solids really good. You ever see the old movies where you want to know if the train's coming? You put your ear on the track and you can hear it through the track, through the metal track, before you could actually hear it through the air, right? So you don't have to worry about getting run over by the train because you'll have plenty of time if you can hear it through the metal. So it is mechanical. It needs a medium. And if you've ever seen the demo, I did it with my class where you got the bell and you put it in a vacuum, you suck the air out, and you can hear the sound goes away. Okay. So if I have something vibrating, but it doesn't have a medium, air or something like that to hit, it doesn't travel as sound. Sound doesn't travel in space. So it is definitely mechanical. It's not electromagnetic. It's not an oscillating electrical magnetic field. It is mechanical and it is longitudinal. It is mechanical and it is longitudinal. Sound vibrates in the direction it propagates, parallel to the direction it propagates. It does not do this, even though sometimes we kind of draw that to indicate sound. We might say, oh, there's a higher frequency sound, like that, and we go like that. But that's not how it travels. Sound isn't going like this. It's not going like this. It's actually, the air is compressing and then relaxing, compressing and relaxing. So it's actually more like this. Really difficult to draw. So we may have a bunch of things bunched up and then spread out and then bunched up and then spread out and so forth. Really difficult to draw, actually. So the answer is, what do we got? Longitudinal and mechanical. Number 2, it is 2. Longitudinal and mechanical. All right. An electrical force of that many newtons exists between 2-point charges. If the distance between the charges is doubled, the new electrical force will be. All right, this is one of those, this is kind of like proportional thinking here. What we want to do here is we're going to set up 2 situations. First situation, the force of gravity. This is a gravity, oh no, this is an electrostatic force. But anyway, it doesn't matter. Equals K, Q1, Q2 over the distance between them squared. So what we do is we have 2 charges. Q1, Q2, and they are separated by a distance R. And this force, they said, equals 8 times 10 to the minus 5 newtons. All right. If the distance between the charges is doubled, so now we're going to have a different situation. Let's call that force 2. We want to know what the force between them is if we double the distance. So we go Q1, Q2, same charges, but now they're separated by distance 2r. All right. Intriguing. The new electrical force will be, well, let's see what happens. Let's just plug the numbers in, see what we get. All right. K star is the same, the constant, that's a lowercase k. Q1 is the same. Q2 is the same. But now it's not r, it's 2r. Now be careful. It's the entire quantity squared. All right. So let's simplify this a little bit. Let's distribute that. We have our K, we have Q1, Q2, 4r squared. We got to square the 2, and we got to square the r. Why is that? Well, what is 2r squared? It's 2 times r times 2 times r. All right, let's get those together. That is, of course, 2 times 2 is 4, r squared. So make sure you do that. Of course, the common mistake would just to say this is 2 times r squared, and that's not true at all. All right, let's get rid of the 4 and go, okay, so this is 1/4 k q1 q2 over r squared. Well, that looks familiar. My memory's not too good, but I remember that from somewhere else. Oh yes, there it is right up there. Like there, that is F1. All right, so this thing right here is F1. I can see that right there. It's right there. So we got 1/4 times F1 equals F2. All right, so what is that? 8 times 10 to the minus 5 newtons divided by 4. 8 divided by 4, I believe, is 2. 2 times 10 to the minus 5 newtons. All right, now, this is what I always want you to do in these problems, because you can get yourself messed up if you get a fraction in the denominator and you're not very good with dealing with that, and you might make a mistake. So what you want to do is you want to go, okay, I started off like this. Now they're farther apart. You have to know that when they're farther apart, there's going to be less force. So you have to make sure your answer is smaller. If it's bigger, that means you made a mistake in the math. So let's see. I'm looking for a smaller. Is this smaller? It was 8 times 10 to the minus 5. Now it's 2. Yeah, that's smaller. I buy that. Let's see what the answer is. 2 times. Oh, I guess the answer is choice 2. A blue lab coat. Oh, I happen to have blue here. Hopefully it writes. This way's west. This way's east. I'm going to make west its head It's traveling in a negative direction in my world. On track collides and sticks with a red lab cart. Oh, I have red too. Nice. This is just coming together. You know, sometimes things just come together. And this one has a velocity this way. And this one has a velocity this way. Always draw a picture. I don't even know what they're going to ask. I don't know what the question is, but draw your pictures. Adjust as you go. You may have to adjust as you go. That's okay. We're flexible people. That's what makes us human beings. We can adjust to situations. That and opposable thumbs. And it sticks. Oh, how convenient. The magnitude of the momentum of the blue cart before the collision is 2 kilogram meters per second squared. All right, so this has a momentum this way equals 2 kilogram meters per second that way. And the magnitude of the red cart is 3. Interesting. They're not they don't have the same momentum. Interesting. And they wouldn't anyways, but they don't even have the same magnitude of momentum. So they have different momenta. What is the total magnitude of the momentum of the carts after the collision? This is a classic conservation of momentum problem. Speaking of conservation laws, let's review what is conserved in nature that we've studied. I think the first thing we may have studied, I don't remember what the first was. Momentum is a conserved quantity. Energy is a conserved quantity, and so is charge. I believe those are the big ones we studied. Can't think of any others. All right. So momentum is conserved. This is the before picture. With a conservation of momentum problem, I would always have a before and after picture. Kind of ran out of room here, but that's okay. We're going to draw it smaller. All right, they stick together, and then they do something. This is after. Now they want to know, what's a momentum? All right. Well, I know the direction, but let's say we didn't. Let's pretend like we didn't. So what we want to do is let's write our conservation law, and I believe this is in your reference table. P before equals P after. All right. I remember momentum. Let's remember what momentum is. It's a vector for one thing. And now with my classes, I always put vector signs above vectors. The Board of Regents doesn't do that. Don't know why, but they don't. So momentum as a vector is an object's mass times velocity, which is a vector, and these two vectors are in the same direction. So the momentum is in the direction of the velocity. So P before equals P after. Always do that. Always write that out. You're gonna, especially on a long answer, you're gonna have to write that to get full credit. But you want to do it anyway. State the physics. I always say, state the physics. P before. So we had the momentum of this thing, which is 3 kilogram meters per second. Now, this is where people are going to mess up because they're going to forget that it's a vector and they're just going to start adding numbers and just whatever. You can't just do that. We're going to treat this like a scalar operation, but it is a vector operation. We're actually adding this vector and that vector. This is going to be 3 kilogram meters per second. This is going to be negative 2 kilogram meters per second because it is traveling west. West is negative and east is positive. Always do that. So 3 kilogram minus 2 equals the momentum afterwards. And I don't even think I need my calculator for this. So this is positive. So this is 1 kilogram meter per second. And because it's positive, it is east. East. This is P after. Oop. P after is 1 kilogram meters per second east. Oh, they just asked for the magnitude. The magnitude, I guess it's 1. 1. You didn't need east, but you should know that. You should know it's east, right? Really what we're doing here, keep in mind, what are we doing here? We're actually doing a vector addition. We would have, like this one, is we would actually measure this to length. This is 3 kilogram meter per second. And we would add to that tip to tail, the other vector, go like that. It's coming back like that. That's 2 kilogram meters per second. And then the resultant is from where you started. We started here to where you ended, and that is going to be 1 kilogram meter per second. That way, which is east. All right. Beauty. Don't forget your vectors. The reason we add the plus and minus is if they're in a straight line, rather than having to draw the vectors, we use a proxy. We use the negative to mean that way and the positive that way. It just makes it easier. And that's why when vectors get more complex in a more advanced physics class, you will break them into their x, y, and z components. But you don't need to do that in this class because they're going to keep it simple in the Regents exam. So there you go. Momentum. It's a vector. Momentum is a vector. It's also a conserved quantity. Two very important things in physics. Yeah, all right. The diagram below represents the path of a thrown ball through the air. A thrown ball. Seems kind of awkward. All right. Which arrow represents direction in which friction acts on the ball? Well, friction is this thing that opposes motion, right? So let's take a look at our ball. We got our ball, and that's a parabola, by the way. That's the motion of an object. That's a trajectory of an object that is in free fall, that is given a horizontal velocity. It's always going tangential to the motion. So this sucker's got a velocity this way, right? It's got a velocity. That's a got a velocity that way. It's going this way, and resistance, air resistance, or in this case, what they call it, friction. I don't know. Is it friction? I don't know why they're calling it friction. I usually don't associate it with something traveling through a fluid as maybe being friction. But anyways, okay, so it's friction, I guess, and it's going this way. Friction always opposes motion, so the force of friction must be opposite the velocity, so the frictional force must be this way. The drag, I prefer to call that drag. Drag, man. The drag. Choice 2, I guess. So choice 2, that's opposing the motion, the friction is that way. All right. So you need to understand the velocity, and friction always opposes motion. So that is 2. Friction always opposes motion or an attempted motion. A magnetic field would be produced by a beam of what? All right. What caused magnetism? Well, it's relative motion of charge is what causes magnetism. So we need some charge objects. We need something moving, some charge thing moving. X-rays, that's electromagnetic radiation. That's photons. Photons don't have charge. Don't have charge. Gamma rays, made out of the same stuff as as X-rays. No charge. Light is neutral. There's no charge on it. Protons, they have positive charge. Yes, there can be a magnetic field associated with moving protons. Neutrons have no charge, so the choice is 3. Magnetism. Magnetism is caused by motion of charge. Relative motion of charges between different charged objects causes magnetism. So we would only get an electric field with protons. You need charge. Those other things don't have charge. All right. The diagram below represents the electric field in the region of 2 small charge spheres, A and B. What is the sign? All right. The direction of the electric field is defined, and you need to just memorize this, as a direction a positive test charge would experience in the presence of that field. So here's my positive test charge. Right here. It's positive. It's got a plus on it. And so what you want to do is you want to go like this, and you go, oh, it's a track. It's going to experience a force like this. It's getting pulled in. Now we need to understand the rules of charge. The rules of charge say that opposite charges attract, like charges repel, and Well, those are basically the rules. And if you have an object, an extended object in the presence of a charged object will polarize and be attracted to that charged object. So if you see two things attracting, you know that either they're opposite charge or one of them's neutral and the other has a charge. And if they're repelling, you definitely know they have the same charge. But anyways, let's take our little test charge. This has to be a small charge. I made it big so you can see. So it's being pulled in. So if this is positive, then, and it's attracted, these must be negative. All right. Both of them are negative because I see that either way, when I put it, it's going to feel a force coming in like that. What is the sign? They're both negative. Which one's that? Three. They're both negative. Okay, so if you got one of these electric field problems, I would recommend ripping off the corner of something and maybe not your answer sheet because it may invalidate it. They got the rules, I don't know. Say the corner's missing, invalid. Put a little plus on it. That's your test charge. Put it there and do a thought experiment. You know that like charges repel and opposites attract. And since I can see that's attracting, they must be opposite of my test charge. And there we go. And these must be repelling each other, but that's a different story. La 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 la. Elbows were old. All right, here we go. Draw another picture. I hope you're drawing pictures. Did I have mentioned that I would like you to leave right now if you're not drawing pictures? Right? Don't even, I wouldn't, if you're not going to draw pictures, don't show up to the exam. Just stay home. Stay home. It's not worth it. You got to draw pictures. We got a box. All right, you got a box. And a horizontal force of 20 newtons eastward. All right, sways east. All right, 20 newtons. Putting 20 newtons of force on that. Causes a 10 kilogram box to have a displacement of 5 meters. All right. So this thing's got to place. Remember, 5 meters. Why did I draw that as an arrow like that? Because that's a vector. Displacement is a vector. Started here, went there. That's my displacement vector. That's different than distance. This also travels a distance of 5 meters, but 5 meters doesn't take into account direction. This is displacement. All right. So we got a force of 20 newtons this way and a displacement of 5 meters that way. The total work done on the box by this 20 newton first. All right. The Board of Regents does something really nasty in this thing. If you look up, if you just like Mr. Plug and Chug or Mrs. Plug and Chug or Cousin Plug and Chug, you say like that. You go, work is force times distance. But no. Now, work is a form of energy. It is indeed a scalar. But these have to be vectors. This is force times displacement. And actually, technically, it's the vector dot product. Because the force and displacement have to be in the same direction. Right? They have to be in the same direction. Conveniently, in this case, they are. They are. We have 20 newtons and 5 meters. They're in the same direction. So I'm just going to say 20 newtons times 5 meters is 5 times 10, 40, 5, you got to carry the 3 in, it's 100. 100 joules. 100 joules. Yeah, choice 2. Now, let's make it a little more difficult. Let's say they said this. Let's say they said this instead. They said, all right, let's go 20 newtons at 30 degrees. All right, now my 20 newtons isn't in the direction of displacement. Some of it is. Some of it is, certainly. So we're going to want to break this into its, this could be broken into its components. We got the force this way, and we can think of this as two forces. This is both pulling up and it's pulling out. And here we go. This is the hypotenuse of a right triangle. So this is going to be the force in the x direction is going to be 20 newtons times the cosine of 30 degrees. All right. I'm going to make it easier on myself. I'm going to make it easier because I don't feel like pulling out my calculator. Let me try this. Let's say 60 degrees. Just made my life easier. Why? Because the cosine of 60 degrees is 0.5. 60 degrees. There we go. All right, I believe that's 10 newtons. All right, so in this case, they didn't ask this, but if they did, the work in this case being done by this rope or whatever is pulling on it would be work equals force that's in the direction of the displacement, which is 10 newtons times 5 meters equals 50 joules. Joules. All right. So there you go. The answer was 100, though. The answer was 2. Beep. All right, we got a block. Yeah. It is at rest. Horizontal frictionless surface. Frictionless. The magical frictionless surface is accelerated by a constant horizontal force of 5 newtons. That's 0. That's time 0. And then sometime later, we'll call that time 1. How much is the kinetic energy of the box? So we still have that 5 newtons there. Increased. We know that the energy at 0 equals the energy at 1. And the complete statement for conservation of energy, although it's not given on your reference table, I would recommend you know it. Especially if you're going to be taking physics in your future. It says the kinetic energy you start with, plus the potential energy that you start with, plus any work that is going to be done between the beginning and the end equals, and I call that external work, kinetic energy at 1, plus the potential energy at 1, plus any internal energy. All right, and the internal energy, of course, is going to be friction for the most part in this class. Friction. All right, it's frictionless surface. There's not going to be any internal energy. I'm going to say the potential energy is 0 on ground level. It stays at 0. There's no change in height. So our potential energies go away. So it looks like that this work that is done is going to equal the kinetic energy at 1 minus the kinetic energy at 0. All right. So the work changes the kinetic energy. And they said that it did 15 joules of work was done by that. And they said it started at rest, so the kinetic energy at 0 is 0, and the work done, they said, was 15 joules. So it looks like, just rearranging this, the kinetic energy at 1 equals the work done, I call it external work, plus the kinetic energy at 0, which is 0, equals 15 joules. 2. The answer is 2. All right. I'm going to get some hate mail, some hate comments on YouTube saying, hey, I hate the way you complicated that problem. It didn't have to be that complicated. Well, all I can say is, stop hurting my feelings, man. I'm just trying to do my job here, you know. I'm sorry you think it's too complicated, but I like to be complete in my explanation. 2 objects, A and B, are held 1 meter above the horizontal ground. The mass of B is twice the mass of A. All right. Here we go. 2 objects, A and B. Here's A. And what would B? They're both held 1 meter. The mass of B is greater. Twice as great, I guess. All right. Same height. Above the horizontal ground. The mass of B is twice. So, mass of B is 2 times the mass of A. Right? Notice how I made it bigger. I'm proud of myself for that. So, the potential energy at A, they're going to call as PE. Potential energy at B. All right. Well, what is this? M-A-G-H. And these are both height H. Right? That's the potential energy at A. Well, relative to the ground, I'm going to say the potential energy is 0 here. So the potential energy at A is M-A-G-H So what is B? Well, that is MB. G, the same H. But, now this is similar to that earlier question we had. MB is 2 mass A. I'm going to replace that in there. 2 mass A, G, H. Oh, I think I recognize this. That's right there. So this is 2 times the potential energy. Potential energy of B is 2 potential energy because that's what they said this was. Replace that in there. 2PE. What is it? 2. Right? So the potential energy of an object is proportional to its height. It's also proportional to its weight. Remember, mg right here is the weight, right? Don't make that mistake where they give you the weight and you treat it as mass and multiply by g. This is mg is an object's weight, right? Fg is mg. All right. So for a given height, the gravitational potential energy is proportional to the weight. What is the kinetic energy of a 50 kilogram skier traveling at 9 meters? Oh, man. Sometimes. Okay, kinetic energy is the energy of motion, and it's 1/2 mv squared. Where this is speed, that's not velocity, that's speed. How fast the thing going? 10. All right. What is the kinetic energy of a... All right, well, they gave us the mass. 55 kilograms. And the speed is 9 meters per second. What's the kinetic energy? This is a terrible... Another bad marker. I hope you can see that. That's better. All right. This is just plug and chug. 55 kilograms times 9 meters per... Now, don't forget to square that, because I bet you they have... What do you think? What are the chances they have the answer where it's not squared? Well, we got 2,000... Yeah, so the answer is 3. I got 2.23 times 10 to the third joules. Actually, I should only have 2 significant figures times 10 to the 3. When in doubt, give 3 significant figures. Never give 1. Looks like we have 2 and 2. That is infinite precision. I guess the answer is 3. Let's see, were they nasty? And let's see if they gave the answer if I just multiply that by 9. 248. Yeah, that was there. And, it'd be so sad. You go, yeah, nail that one. Yeah, ho. Right? Because they had the answer, they go, I must be right because the answer's there. Well, no, they're tricky that way. A 5.09 10 to the 14 hertz electromagnetic wave is traveling through a transparent medium. That seems to be an awfully specific number. I wonder why. Hopefully it looks vaguely familiar. That's awfully familiar. I believe you look at your reference table. That's our favorite flavor of yellow. I bet we have an index of refraction for that. The main factor that determines the speed of this wave is... What determines the speed of an electromagnetic wave? It is the medium itself, the nature of the medium. Yeah, the answer is 1. We can look at the index of refraction. Index of refraction is the speed of light in a vacuum divided by the speed of light in that medium is the index of refraction. And things are always going to go slower in other media. What really happens when light slows down is the photons go through. They actually get absorbed in the molecule for a short period of time, and then it spits it out again, and it's that delay that gives us this experience of slowing down. That's 16 is 1. It's the medium that determines the speed. In a vacuum, they all travel at c, 3 times 10 to the 8th meters per second. All right. So the medium is what determines the speed of an electromagnetic wave. And that's true of mechanical waves, too. The medium. not the amplitude. All right. 17, a motor does a total work of 480 joules in 5 seconds to lift the, all right. So we got a motor. Here's a motor, and I'll put a little pulley, and let's say it's lifting something like that. Oh, that's a fine drawing. It's doing 480 joules of work. So it's applying a force this way, and there's a displacement this way. So there is work being done. Work, of course, is force times displacement, where the force and the displacement have to be in the same direction. The average power developed. All right, what is power? Look that up in your reference table. Power is the rate at which work is done. 480 joules. They didn't give us the displacement, so they gave us the work though. 4 times 5 seconds divided by 5 seconds. 480 divided by 5. 96. 96. 96. What? So it's 96 what? I know what you're thinking. What? Yes, indeed. Yes. What? Watts. Power is 96 watts. 3. Choice 3. So we have an elevator motor, right? Yeah, we're in an elevator. Yeah. I wonder if they're gonna have an elevator problem in this. All right. Now elevators don't really work like this. But I'm gonna do it. There's a counterweight and all that stuff. But anyway, for this simple problem, let's just pretend it behaves like this. All right. So the power of this motor is 5.8 times 10 to the 4th watts. That's how much power it can deliver. 5.8 times 10 to the 4th joules every second. That's how much, the rate at which it can supply energy. Can lift a total weight of, and let's see. So if it pulls a constant velocity, it will actually pull with the object's weight 2.1 times 10 to the 4th newtons. How fast can this constant speed be? Well, let's take a look at this. Power is the rate at which work is done. But work is force times displacement, where the force and the displacement have to be in the same direction. And displacement divided by time is actually velocity. So this is a force times velocity, as long as the force and the velocity are in the same direction. Velocity, therefore, equals power divided by force. And the power is 5.8 times 10 to the 4th watts, joules per second, divided by 2.1 times 10 to the 4th newtons. 2.76. Actually 2.8, because they only gave 2 significant figures there, times 2.8 meters per second. Let's make sure those units work out. Let's do a unit figuring out review. A watt. So power is work divided by time, or joules per second. All right. Well, what's a joule? Well, let's take a look at potential energy, because potential energy is in joules, equals mgh. All right. Well, what's potential energy? Potential energy has units of joules. Mass has units of kilograms. G is meter per second squared, and H is in meters. So a joule must equal a kilogram meters squared per second squared. See what I did there? You just get the relationship. You know that potential energy is in joules, mass is in kilograms, G is in meters per second squared, height is in meters. So there we go. All right, so then this must equal, a joule per second is a kilogram meter squared per second squared. And then we have the second. All right. So we end up with, so that's what a watt is, I guess. That's what a watt is. That equals a watt, because that's what power is. All right, so we had kilogram meters squared per second cubed is watt divided by Newton. What's a Newton? Well, let's see. I know force is in newtons. Equals mass. I know it's in kilograms. Times acceleration, which is in meter per second squared. So a Newton is a kilogram meter per second squared. So let's take this. A watt is a kilogram meters squared per second cubed divided by kilogram meter per second squared. Kilograms go away. One of the masses goes away. And it looks like we end up with 1 second. So that is a meter per second. Beautiful. Beautiful. So we ended up with meters per second. It worked out. That's fantastic. I love it when the physics works out. All right. A stationary police officer directs radio waves emitted by a radar gun at a vehicle moving towards the officer compared to the emitted radio waves. The radio waves reflected from the vehicle and the received by the radar gun have... All right. Here we go. Got a car. Got a radar gun. Like that. Got a police officer. Better give him a hat. Oh, man. There's an officer's hat if I've ever seen one. All right. Here's a car. Headlights. Got velocity this way. All right. He sends electromagnetic radiation at the car. It has a certain frequency. All right. I'm showing you the wavelength. Now, when it reflects, should have drawn them more even. When it reflects when it's coming this way, because the car's going this way, every time the new wave hits it, it's a little closer than the previous one. So what happens is the waves that come off this thing are closer together. They're at a higher frequency. This is the Doppler effect, right? It's like Doppler radar, all right? So it comes back higher frequency. And what was the question? Compared to the emitted radio waves, the radio waves reflected by the vehicle have a shorter wavelength. Let's see, what do they have? They have a shorter wavelength, a higher frequency, and therefore a lower period, because frequency and period are reciprocals. So a higher frequency, right? Frequency and period are reciprocals of each other. The way you can keep, it can be real easy to confuse period and frequency. What you want to keep an eye on is the units. Now, period is a capital T. Now that should be a big clue to you what the units need to be in period, and that is, of course, seconds. This is a measurement of time. So make sure that if you have something in units of seconds, if they're talking about waves, that you're dealing with a period. If it's 1/seconds, it's frequency, because they are reciprocals of each other. A light wave strikes the moon and reflects towards the earth. As the light wave travels from the moon to the earth, the wave carries. Right, we got the moon, we got the earth, and we got a light wave. Let's draw it as a wave. Right? As the light travels from the moon to the earth, the wave carries energy only. Yeah, it certainly gives us energy. Matter? No matter. No matter gets transferred, right? These are oscillating electric and magnetic fields. And waves in general don't transfer matter. They transfer energy. Both energy and matter? No, neither. It's energy, right? Waves transfer energy. The time required to produce one cycle of a wave is known as the wave's... Oh, there we go. There we go. The time. Time for one wave. Well, that's capital T. That is period. Period. The time required to produce one cycle of a wave is the period. 3. Right? A magnetic compass is placed near an insulated copper wire. When the wire is connected to a battery and current is created, the compass needle moves and changes its position. Which is the best explanation? All right, now we need to understand two things. One, what causes magnetism, and that's moving charge. In a permanent magnet, it's the spin of the it's electron spin in spin alignments lining up that give you the magnetic field. But in this case, this is actually charge moving through a wire, causing the magnetic field. Now, the other thing we need to understand is what is a compass. Now, you have a compass, and it looks something like this, like that, and it's usually got one colored side. This the side that's marked as north, right? You can have one side that's colored, and it's going to be said that's the north pole of a magnet. This is actually a magnet. This is actually like a little bar magnet on a needle, and so that's the north side. This is the south side right here, and that's all a compass is. Which is the best explanation for the production of the force? So if you had, when you're doing these magnetic problems, just like when you're doing electric field problems, I recommend that you make a positive test charge. With magnetic problems, if you're dealing with magnetic fields, I would, that's the north pole of a magnet. I would think about a compass needle. So there's my compass needle. Right there. And if I had a magnetic field someplace in space, let me get rid of this. If I had a magnetic field someplace in space, so here's my magnetic field, like that. The symbol for magnetic field is B. If I had my compass near here, it would align with the field. Right? That's the definition of the direction of a magnetic field is the direction a compass would point, the north pole of a compass. So anyway, why does this thing turn? Why does it experience a force? And number one, the copper wire magnetizes the compass. No, the compass is already magnetized. What kind of a silly statement is that? It exerts a force. No. The compass needle magnetizes the copper. No. The copper wire has magnetism because it has charge moving through it. The insulation on, I'm not liking this one. The insulation on the wire becomes charged. No, it doesn't. Which exerts the force, and no. Electrostatic charges do not affect a compass, right? There's no magnetic field associated with a charge buildup. It's only moving charges that we see magnetism. The current in the wire produces a magnetic field, yes. That exerts the force on the compass, yes. That's what happens. All right. And it turns out, of course, if you had a wire with current going through it, we do use the right-hand rule, and that sets up closed loops around there. Anyways, I don't know if the Board of Regents actually tests that, but I did. A beam of monochromatic light of frequency 5.09 times 10 to the 14 hertz has a wavelength of 589 nanometers in air. What is the wavelength of this light in lucite? All right. So what's that frequency about? Well, they gave us that because, so now we can use the index of refraction. What is the index of refraction in lucite? Index of refraction in lucite is 1.50. We got a wavelength of 589 nanometers. What is the wavelength in lucite? What does that equal? And actually, I should have put this here, air. And also, we know the index of refraction in air is 1. All right, the reference table has this handy-dandy relationship. The index of refraction in 1 over the index of refraction in 2 equals the wavelength in 2 divided by the wavelength in 1. Basically, we want to know the wavelength in lucite. Let's make that lucite. All right? So I'm going to go index of refraction in air over the index of refraction in lucite equals the wavelength in lucite divided by the wavelength in air. So all we need to do is solve this for index of wavelength in lucite. So the wavelength in air is 589 nanometers times index of refraction in air divided by index of refraction in lucite. All right, let's see what we got. So it's 589 nanometers divided by 1.5. 393 nanometers. 393 nanometers. Is that an answer? Yes, it is. And in fact, it's choice 2. When a wave travels from one medium to another, it's important to understand that the frequency will remain the same. The speed can change and the wavelength can change. So basically, when it goes from air to lucite, the speed is going to go down. Therefore, the wavelength is going to get smaller. If the amplitude of a sound wave is increased, there will be an increase in the sounds. All right, so as the wave gets bigger, that increases its energy, which in the case of sound would be its loudness. With light, it would be its brightness. So as the amplitude of a sound wave increases, there is an increase in the sound's loudness. 1, loudness. Pitch. Okay, pitch is how high is a high pitch, is a low pitch. And pitch is determined by frequency, right? I like to think of frequency as like the flavor of a wave. So pitch is really what determines what different sounds sound like. Amplitude does not affect a wave's velocity, nor does velocity affect amplitude. All waves travel at the same speed when it's in the same medium, and at least mechanical waves. And wavelength has to do with pitch also. 25, we have a parallel plate capacitor. Now, they have parallel plates. Now, parallel plates usually are never like this, right? They're usually very close together, and they're very wide compared to the distance between them, but I don't know. They like to do that to give us plenty of room. So point P. Now, the important thing to understand when you have a parallel plate, this is a parallel plate capacitor, it looks like, that you have electric field lines. And what's important to understand is you need to be able to draw them. Let's go through that thought of experiment, what the field would look like. I'm going to use red for the field lines. Red. So if I took a positive charge here, it would experience a force downward. It would repel and attract and repel and attract and repel and attract. So it would actually, the field line would be straight down like this. They would be evenly spaced. Now, what does the spacing between the field lines indicate? The spacing between the field lines indicates how strong the field is. So anywhere in between these plates, although these are ridiculously far apart, the electric field is going to be equal no matter where you are. It's going to be constant between these plates, a constant electric field. So you should draw it that way. These are maybe a little too close together. Make sure if you're drawing these that you take some time. I'm not going to do it. I'm not going to take time. I don't have time. I'm a busy man. But on a test, you want to make sure they're clearly equally spaced to show that the electric field is equal no matter where you are in between these. So it doesn't matter where you place an object in here. It's going to experience the same electrostatic force because the field is the same everywhere. If you get closer to the plates, the force doesn't increase. Not that they ask that, but they will on exams. Compared to the magnitude and the direction of the electrostatic force on an electron at P, the electrostatic force on charge is what? All right. The electrostatic force is going to be the electric field times the charge, right? So the electric field is the same whether it's you put a. Now the electric field is what it is. They didn't tell us how much it was here, and if I put a proton here, it's going to feel a force depending on its charge, and electron's going to feel a force. Now the magnitude of the force has to do with the charge, and the charge on a proton is positive 1.6 times 10 to the minus 19 coulombs. The charge on an electron is negative 1.6 times 10 to the minus 19 coulombs. So they have the same magnitude of charge. So protons and electrons have the same magnitude, so they're going to experience the same force. Now, keep in mind there is something very different about the characteristics of a proton and electron, and the most pronounced one is that a proton has much more mass than an electron, but they have the same amount of charge. So they're going to feel the same force, but if they asked about acceleration, the proton will accelerate at a much lower rate than the electron will, because the electron has about 1,000 times less mass, something like that. So the electrostatic force on a proton placed at point P has the same magnitude and same direction. No, the directions will be opposite. If we think about this, if I put a proton here, like that, it's going to feel a force that way. And let me make it bigger so you can see. So here's my proton. If I put an electron there, it's going to feel a force this way. The forces will be equal in magnitude, opposite in direction. So there we go. What answer is that? Same magnitude, but the opposite direction. That's choice 2. Choice 2. What else did they say? A greater magnitude, but the same direction. Okay. But nonsense. Nonsense, I tell you. The effect produced when 2 or more sound waves pass through the same point simultaneously is called interference. This is a unique wave property. When 2 waves exist at the same point at the same time, they interfere with each other. Sometimes they come together and create a larger wave, in which case, larger wave than either one of them, that is called constructive interference. And when they come together to produce a smaller wave, that's destructive interference. So the answer is 126. The effect produced when 2 or more sound waves pass through the same point simultaneously is called interference. Didn't have to be sound, any kind of wave will do that. A gamma ray photon and a microwave photon are traveling in a vacuum. Compared to the wavelength and energy of the gamma ray photon, the microwave photon has, all right, if we take a look at our reference table, we see that we got our electromagnetic spectrum. It's this big long line. And in here we got visible, and then they break it out like that. And over here they have high frequency, and if you notice over here, they have lower frequency. And we've learned with the photoelectric effect that the energy of a photon is proportional to the frequency. It's Planck's constant times the frequency. So, and then if we looked over here, we had all this nasty stuff, right? We had gamma, and we had X-rays, and what else do we have? We had ultraviolet, all these stuff that messes you up, gives you skin cancer, stuff like that. And then we had, over here, we had infrared, and we had microwave, and we had radio, right? These are more benign. They have less energy per photon. What's the question? A gamma ray photon and a microwave photon travel in a vacuum. Compared to the wavelength and frequency of a gamma wave photon, the microwave... Oh, the one thing that is the same, so we have high frequency, low frequency. This means we also must have short wavelength, and you can see that on the reference table. Short wavelength, long wavelength. But what is the same for all of these in a vacuum? They all travel at c, which is 3 times 10 to the 8th meters per second. They all travel at that speed in a vacuum. That is the speed of light in a vacuum. And in fact, as far as we know, nothing in the universe can travel faster than that. That's this sort of a cosmic speed limit. Compared to the wavelength and energy of a gamma ray photon, so we have gamma, We have gamma. And I would recommend you do this when you're ready so you don't get them backwards. Microwave. Microwave. All right. And what are they talking about? They're talking about wavelength and energy. All right. So this has high energy, low energy, relatively low, relatively high, and wavelength, short wavelength, long wavelength. So I would write these out. Make sure you don't get those, so you don't get things backwards. Write them out. You have your reference table. Look at that electromagnetic spectrum. Okay, so compared to the way that they get the microwave, so we're answering about the microwave. So I'm going to circle that so I don't mess up and get it backwards. Microwave has less energy and longer wavelength. I guess that is choice 3. Less energy, longer wavelength. All right. Are you looking at your reference table?
Regents reference table.
Excellent. So standard model of color neutrino is a type of, that is a lepton. Lepton. It's right there in your chart. I don't know what to tell you. Doesn't get much easier than that. All right, which combination of quarks produces a neutral baryon?
Regents
A neutral baryon. Okay, baryons. If you take a look, a baryon is going to be 3 quarks. That's it. 3 quarks. All right. Now, if it's neutral, it's going to have 1 quark that is 2/3 elementary charge, then a negative 1/3 elementary charge, and a negative 1/3 elementary charge. That will give us a neutral. So which one of these would give us? A charm top? No. Charm top, no good, because that's going to give us a 2/3 and a 2/3. A down strange bottom, no, that's negative 1e. Up, down, strange would do it. Up, down, strange, that would do it, I believe. Up, charm, and top will not do it. Up, down, strange, because that was a 2/3, minus 1/3, and minus 1/3. Now this is neutral. It is not a neutron though. A neutron is made out of only ups and downs. Protons and neutrons are both made out of ups and downs. So a neutron would be an up, down, down. A proton would be an up, up, down. When a 2 times 10 to the minus 16 kilogram of matter is converted into energy, how much energy is released? All right, this is Einstein's idea. E equals mc squared. Remember when I did that? I said E equals mc squared. All right. And what that tells us, since this is such a huge number, that a small amount of mass can give a reasonably large amount of energy. Let's use this to solve. All right. So we have a mass of 2 times 10 to the minus 16th kilograms. And C is 3 times 10 to the 8th meters per second. And we're going to take E equals mc squared. And we're going to calculate how much energy. 2 times 10 to the minus 16 kilograms times C squared. Don't forget the square. Times 10 to the 8th meters per second squared. All right. Let's see. This could be 18 times 10 to the 6, 10, 18. 18 joules, I believe. Yeah, 2. Choice 2. They gave it in scientific notation 1.8 times 10. Notice what they did. They gave an answer where if you forgot this, if you forgot to do that, that answer's there, and they're going to mess you up. That's what they're going to do to you. That's what the Board of Regents, that's their dirty trick. All right, so they're going to do that to you. Make sure you, just because an answer's there doesn't mean it's right. Don't get too cocky. A ball is hit up with an initial velocity of 28 meters per second. What is the speed of the ball 2.2 seconds after it hit? All right. So sometimes later, is it still going to be going up? Let's see. I'm going to do a quick estimate. So that's about 30 meters per second, right? It's about 30. At what rate is this going to slow down? Well, about 10 meters per second, because acceleration, of course, is negative 9.81 meters per second squared, or 9.81 meters per second squared, which is about 10, right? That's about 10, downward. All right, so if that's going 30, how fast is it going after 1 second? Well, it's going to lose 10 meters per second. So after 1 second, it's going to be going 20. After 2 seconds, it's going to be going 10. After 3 seconds, it's 0. So in this case, it's 2.2 seconds. So this thing's still going to be going up. All right. So we want to know, what is the speed of the ball? V initial is 28. V final is question mark. And the time interval is 2.2 seconds. And we also know that it's accelerating down at 9.81 meters per second squared. Keep in mind, this is in free fall. Even though we consider falling down, that's usually the way people think about falling. This is in free fall. In physics, free fall means that the only thing acting on this thing is gravity. And the only thing acting on this thing is gravity. So let's take a look. So we have V initial, V final, acceleration, and time. So I think we're just going to look at a reference table. V final equals V initial plus acceleration times time. I use delta t in there because it's a time interval to remind us of that. All right, so what's V final? Is 28 meters per second plus negative 9.81 meters per second squared times 2.2 seconds. If you didn't have that negative in there, you're going to have some problems. Anyways, just looking at the answer, it looks like it has to be either 1 or 2. I'm guessing 2. 6.42 meters per second. So I guess the choice is 2. Now, if you chose one of the numbers where it was going 22 or 28, if you chose 28, it's like, what? What? Didn't slow down? It should have slowed down quite a bit after 2 seconds. In fact, the only thing I wanted to check is to make sure it wasn't going down this way. It's still going up. Make sure you have that negative on there for your acceleration. Remember, down negative, up positive. A particle with a charge of 3.00 elementary charges moves through a potential difference of 4.50 volts. All right, so we must be in a... they don't say whether it's positive or negative. What is the change in electric potential energy of this particle? All right. So this thing's moving through an electric field, so we have some sort of charged particle. Let's say it's positive. And so this is in some sort of electric field. And we must be moving it this way. Voltage is a normalized energy. If you take a look on your reference table, voltage is energy per unit charge. It's a normalized energy. So let's just solve this for, we want to know what is the change in electrical potential energy. So the energy is going to be voltage times charge. 4.5 volts. Now we have to be careful. These are not standard units. Let's get this into standard units. Let's multiply by ones. All right, so we want the elementary charge to go away. 1 elementary charge is 1.6 times 10 to the minus 19 coulombs. Get off my futon, Dulom. A blast from the past. All right, times 4.8 times 10 to the minus 19 coulombs. 2.16 times 10 to the minus 18 joules. Oh. They gave it to us in electron. I wasn't expecting that. They gave it to us in electron volts. They didn't do, oh, okay. So anyways. So this is easier. 3 elementary charges. 13.5 electron volts, which is 4. Choice 4. I got sucked. Usually they ask you in joules, but they actually they gave us units of electron volts. So the answer is 13.5. If they had asked for joules, it would have been 2.16 times 10 to the minus 18 joules. But they didn't ask for that. Which circuit has the largest equivalent resistance? All right, this is an important idea in electricity. Anytime you add a resistance in a circuit in series, the resistance goes up. You know, if you're blowing through a straw and you add another straw in series, it gets harder. And every time you add another one, it gets harder. Now, on the other hand, and remember I did this in class, if you add another straw in parallel, it gets easier. Every time you give another path in parallel, it gets easier. Resistance drops when you add another path. And in fact, the resistance will always be, if you have a parallel circuit, the total resistance will be less than the smallest resistance. So if we take a look at 1. In series, the equivalent resistance is easy. Just add them up. The equivalent resistance is 8 ohms. So for 2, the equivalent resistance has to be less than 2 ohms because you have a 2 ohm, a 2 ohm, and a 4 ohm. It has to be smaller than the smallest. It's going to be less than 2 ohms. Number 3, it's going to be 10 ohms, right? We just add those up in series. And 4, it also has to be less than 2 ohms because 2 ohms is the smallest. 4. So it looks like 3 is the answer. That's going to have the largest resistance, right? The smallest resistance is going to be 2. And then 4. And then 1. All right. So keep that in mind. In parallel, the equivalent resistance is always smaller than the smallest resistance. All right. You could calculate those. The series are easy to calculate, but the parallel is a little more involved. Keep in mind, in parallel, 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3, right? So R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3, which is fairly involved. And let's practice this real quickly. R1, let's say, is 1 ohm. R2 is 2 ohms. R3 is 3 ohms. What I would do is use the, if you're using the Texas Instrument calculators, really what you want to do is you look at it this way. It's really R to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1, all to the minus 1. So that's what you're going to do in your calculator. You're going to go 1 x to the minus 1 plus 2, hit the x to the minus 1 key, plus 3 times x to the minus 1. And then you're going to hit the equals key. That will not be the answer. That will be 1 over the answer. And then just hit x to the minus 1. And it will take the answer and invert it. And your answer should be less than the smallest, but it won't be ridiculously small. In this case, those 3 resistors in parallel would be 0.55 ohms. All right? There we go. If we had those three resistors in parallel. A transverse wave is moving toward the right in the uniform medium. The point X represents a particle of the uniform medium, which diagram represents the direction of the motional particle X. All right, this is Dot on a Wave. Get the music going. All right, so we have velocity this way. We have wave this way. All right, so a moment later, this thing's going this way. It's going to be, this thing's going to move here. It's going to be higher. So this thing's actually moving like that. That's the direction of particle X, which is 3. Because this thing's going this way. So a moment later, it's going to be at this higher point in the wave. So it's up. It's going up. Up, 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 up. Down on the wave. Which diagram represents the magnetic field lines between two north poles of a magnet? All right, if I want to understand the magnetic field lines, I'm going to grab my compass. Where'd my compass? Here it is. Here's my compass needle. All right, if I put my compass needle here, it's going to be really confused. It's like, oh, which way do I point? All right, the field is very small in here, so there shouldn't really be any field lines. But on the other hand, if I put it here, north, is it going to track to north? No way, no way, no, no, no. It's going to want to go away from here. So if I put it here, it's going to start going out like that. And then it's going to see that one. So it's repelled by that one. And then it's going to, and then, oh, we only want to know here. Oh, on a diagram. All right, so here, it's going to want to go out, right? The south of the compass is going to track to the north. So it's going to start out like this. But it doesn't want to keep going that way because it sees that. So it's going to go like that. And then if I put this here, which way does it want to point? I'll point that way. But it does not even keep pointing that way because it sees that other one. It's going to go like that. And then it's going to go like that. And we got symmetry. Symmetry. Anyways, so I'll go something like that. I guess that is 4. I guess that's choice 4. All right. That is the end of the multiple choice. I hope you did well, and maybe there'll be the rest of the exam. I don't know if I can get my act together. This takes a long time to do. You'd be surprised. So maybe the rest will be here later. I don't know if it'll be in time for this year's exam, but it will exist at some point, I'm sure. Good luck.
It's 3 Physics.